Assalamualaikum warahmatullahi wabarakatuh and good morning to whoever watching our video. Today our group will be presenting our project titled Smart Monitoring in CNC Machine for the subject Condition Monitoring in Machining. In this presentation, we explain how smart monitoring can help detect machining problems by using vibration, noise and temperature data. Before we begin, let me introduce our group member. My name is Faizuddin BMIM, together with Amri Kwan, Muhammad Alif Hadari, and Evan Bryan. Okay, now let's move on the introduction. The main purpose of the project is to monitor the machining process and detect chatter before it becomes a serious problem. Our objectives are to measure vibration, noise, and temperature during machining, determine the chatter threshold, and compare the performance of three different materials, which are Teflon, aluminium, and mild steel. We also compare the result between CNC milling and CNC lathe machines. Okay, smart monitoring is important because it helps detect problems early, improve machining quality, reduce tool wear, and prevent machine damage. Okay, now let's move on to the experimental overview. For this project, we use two machines, which are the CNC milling machine and the CNC lathe. The material tests were Teflon, aluminium, and mild steel. To build our monitoring system, we use an ESP32 38 pin as the main microcontroller. Its job is to collect data from all the sensors and process the information in real time. For vibration monitoring, we use the ADXL 345 accelerometer sensor. For noise measurement, we use the INMP 441 digital microphone sensor, and for the temperature monitoring, we use the DS18B20 temperature sensor. These three sensors work together to monitor the machining condition and help detect chatter during the machining process.
Hi, my name is Evan Bryan and I will continue this presentation. This graph shows the result for Teflon. We can see as the depth of cut increases, the RMS vibration also increases. Chatter starts at 1.3 mm. This means Teflon is the most stable material because it can handle higher depth of cut before chattering begins. Next is the result for aluminium. For this graph, we can see the same trend. As the depth of cut increases, the RMS vibration also increases. Chatter starts at 1.1 mm. This means aluminum has medium stability and more stable than mild steel but less stable than Teflon. Finally, this graph shows the result for mild steel. Again, the RMS vibration increases as the depth of cut increases. Chatter starts at 0.9 mm, which is the most earliest among three materials. This means mild steel is the least stable material because chatter happens at the lowest depth of cut. That's all for my part. Thank you.
My name is Muhammad Alif Hadari, so I will continue for the next slide. Now let's compare the three materials during the lathe process. From the graph, mild steel reaches chatter first at 0.9 mm. Aluminium reaches chatter at 1.1 mm, while Teflon reaches chatter at 1.3 mm. This shows that Teflon has the best machining stability because it can handle the higher depth of cut before chatter happens. Aluminium gives average performance, while mild steel is the least stable. Overall, Teflon performs the best in the lathe process. This graph compares mild steel in the milling and lathe machines. Both machines show a similar vibration pattern and chatter starts at about 0.9 mm. That means the machining process does not change the chatter threshold very much for mild steel. This slide explain how the material affect machining stability. Different material have different properties. Some material can absorb vibration better than others. This help delay chatter during machining. From our result, Teflon is the most stable material because it absorbs vibration well. Aluminium show average performance, while mild steel is the least stable because chatter happens first. In conclusion, material with better vibration damping can improve machining stability and reduce chatter. Next, this graph compares mild steel in the milling and lathe machines. Both machines show a similar vibration pattern and chatter start at about 0.9 millimeters. This means the machining process does not change the chatter threshold very much for mild steel. In conclusion, Teflon is the most stable material. Aluminium gives moderate performance, and mild steel is the first material to experience chatter during both milling and lathe machining.
Assalamualaikum, my name is Amrikuan Ahmad. So I will continue the slide. On slide 12, we analyze the operating temperature rise for both our CNC lathe and milling machines. As expected, temperature rise steadily with the depth of cut. Mild steel consistently generates the highest heat due to its shear strength. Crucially, even at maximum depth, the total temperature rise remains highly controlled, never exceeding a safe delta of 10 degrees Celsius above ambient. The key takeaway here is that temperature is a lagging indicator. Because heat boosts up gradually, we use it for steady state system health monitoring rather than as an instantaneous safety trigger. Now on slide 30, let's explore how we organize this distinct metric into a multi-sensor alarm matrix. To detect machining chatter early, we establish a hierarchy. Our vibration sensor acts the first line of defense, crossing its threshold of 0.7 G at a depth of cut of just 0.9 mm. Our noise sensor triggers second, hitting its 85 dB limit at 1.1 mm. Meanwhile, temperature acts as our third layer and is never exceed. By combining vibration, noise, and temperature, we don't rely on just one data point. The sensor fusion dramatically improve our chatter detection accuracy. On slide 14, we translate our multi-sensor data into actionable operational threshold, green, yellow, and red zones. The green zone represents stable safe machining. The yellow warning zone is triggered when vibration cross 0.7 G or noise hit 85 dB, signaling that chatter is imminent and operators should be alert. Finally, the red zone indicates a critical state where immediate action or machine shutdown is required to prevent catastrophic tool failure. This visual zone simplifies real-time decision-making on the shop floor. Now on slide 15, we provide our constraint production recommendations, balancing high throughput with machine safety. To maximize our material removal rate without triggering our warning zone, we have optimized the relationship between feed rate and depth of cut. For toggle material like mild steel, we recommend a more conservative feed rate to keep vibration below the 0.7 G limit. For softer materials, we can aggressively scale up. This optimization ensures maximum productivity with minimal machine downtime. Lastly, let's summarize all our findings. For last slide, present a complete summary of our condition monitoring framework. This table consolidates all our critical thresholds for Teflon, aluminium, and mild steel across vibration, noise, and temperature. By standardizing these parameters, we have created a robust, automated predictive maintenance strategy that protects our CNC machinery while maintaining optimal cycle time. Thank you.
To conclude, there are three important lessons from this project. First, material properties have a strong influence on machining stability. Second, Vibration is the best parameter for early chatter detection because it responds faster than noise and temperature. Finally, combining multiple sensors provides better monitoring and helps prevent machine damage. That concludes our presentation. Thank you very much for your attention. Assalamualaikum. Bye bye.